Yeah. I'm a little bit worried because I think we've got a bouncer in the room. Is there something I don't know? Okay, so my name's Dave Chinner. I work for Red Hat and I work on XFS most of the time. Just to start you all off, I don't mind people stopping and asking questions while I'm in the middle of talking. Anybody who wants to heckle, you're more than welcome to. If we can get a flame war going on between different sides of the room, that's even better. Okay, so basically talk Linux file systems, where do they come from? I'm not going to look at every single Linux file system. We'd be here until this time tomorrow if we did that. All right, so which key makes this work? One of these. Might be. There we are. Okay, so what we're going to talk about here today, I'm just going to go through a few things. The motivation for the talk, because it's interesting where this came from. Our file system fundamentals. I'm going to skip that bit if everybody knows the basic concepts that I'm talking about. I'm going to go through a brief history of different file system technologies so you can get an idea of where the different file systems I'm talking about actually come from in the history of things. Give you a brief overview of when Linux file systems appeared and disappeared, and then go through things in a little bit more details, who, what, when, and so on. So that's basically what the talk is going to be. Yeah, so the motivation came from a paper that was presented at the File Systems and Storage Technologies Conference earlier in the year. Oh, it's actually last year now. This paper was awarded Best Paper of the conference, and it was a study of the evolution of Linux file systems. They took a 2.6 Git tree and basically looked at all of the commits that had occurred from several different file systems and classified them. It was actually a really good piece of work, but I had some questions as a result of it. You know, like I said, it was brilliant, but there was a focus on bug fixes and, you know, what had actually gone wrong with file systems and how they'd been fixed. And it was more of a study on, how do you describe it? How often things needed to be fixed. The classification was done by manual code analysis, so there wasn't anything amazingly special about that. And it turns out that it's very difficult to do anything automated. But they ignored features. The majority of the changes that actually go into file systems were just completely ignored. And they didn't attribute it to anyone in particular. It was just, here are the changes that were made. And like I said, it only considered 2.6 kernels, so it didn't go a long way back in time. But what you ended up with from this talk was a few graphs that demonstrate exactly what they were looking at. So you can see here the file systems, what type of patches went into the file systems, whether they were maintenance, whether they were feature patches, reliability fixes, and so on. And of the bug fixes, whether it was a memory corruption bug or a concurrency error, like a deadlock that was being fixed, a semantic error, like, you know, well, not really a syntax error, but just getting the code flow wrong, the logic, that sort of thing. So you can see that there are a lot of specific types of bug fixes that were actually made, and so on. But what intrigued me was, as you can see, this tiny little bit here, that much feature work in XFS since 2.6, that doesn't seem like an awful lot. But what it turns out, this is commits, and not the amount of change that's actually happening in the file systems. So,
You mean number of commits?
Number of commits, that's this number at the top, 2004. Yeah, so 2004 for XFS, 1100 for X4, and so on. So that's the total number of commits into those file system directories.
But not the number of lines?
No, not the number of lines. So going from that, there's other classifications. What release did they actually occur in? And so once again, you've got the different types of bugs that were fixed and what releases they were fixed in. And I sort of looked at that and looked at the XFS one and said, what happened just there? Why did we fix 40-something bugs way above all the others in that one release. And it turns out that the reason we did that was a result of a paper that these same guys released in 2007 about errors in the file system and how we weren't handling if error. And so that was fixing all the error paths that they pointed out were wrong. It was that insight that led to me thinking, so where have all of these file systems come from? These graphs don't tell the story. They tell part of the story, but they don't tell the whole thing. And it's little things like that that got me thinking on it. So that's where this came from. So, file system fundamentals. Who doesn't know what any of these things are? Inodes are... Everyone knows what an inode are, don't they? Willie? Back in your box. Back in your box. Block maps. Extents. Okay, it looks like everybody has a fair idea of what journaling, copy on write is. You've all heard of these things, so I'm going to skip over all of that because that means I can spend more time just talking about random things. Okay, file system technologies, brief history of them. Okay, so go back into the 1970s and things were fairly primitive. It was not much better than rocks and clubs. That's about what you got out of a file system. Quite often, if there was any sort of organisation in the file system, it was record-based. There was usually a fixed number of records because the file system could only have a fixed number of things that it tracked. Large file systems generally still had the same number of records in them. It's just that each record was bigger, could hold more information. 8-character file names, we all know about those. They were great, weren't they? And really, before we had inodes, there were things like file control blocks that contained information about the file, maybe the size of it. If you were on a system that knew about users, who owned the file? Not much more than that. And there was absolutely no directory structure whatsoever. If you're lucky, you had a file system that had a couple of different regions or a couple of different tables that you could put files in. And so you could put them in region A or region B or region C. I think CPM was the first to do that. So they were pretty primitive. So early modern history, we're a bit more than ancient history. Hard disks were starting to be widely available. And so now file systems were starting to be optimised for the technology available. So they became sector-based and started having complex cylinder head sector mappings to optimise things. Moved to inode tables. These inode things started to appear, so you now had big arrays to store inodes in, and so you weren't limited to only a few tens of files. You might have 60,000 if you're lucky. Bitmaps started to get used for tracking free space, so rather than maybe having a linked list of records or something like that on disk, single bit for a single block, much more efficient. Would have been, I think, 1984 that Mac OS, whatever it was called back then, introduced resource forks. For you Linux people, you probably know that as an attribute, or an attribute fork. Mac used resource forks. So that's kind of where that first came from. Gives you an idea of how long ago these sorts of ideas were around. And now hierarchical directory structures were starting to appear. You could have a certain number of subdirectories in a directory. They were generally limited in depth and the number of entries that they could hold.
Dave, I thought the resource fork wasn't an attribute. Isn't it a separate stream in HFS? So you have,
Okay, so the question was, a resource fork is not an attribute, it's a separate stream. Basically, an attribute is a separate stream in Linux. It's just limited in size to 64K, whereas on HFS, there's no limitation to the size of it. So you can have an arbitrary number of resource forks, streams, an arbitrary number of attributes. It's just that on Linux, the attributes are limited in size. Okay, so late 1980s, research papers started to talk about optimising the number of seeks as you walk through directory structures and free space maps and things like that. And they started talking about the importance of logarithmic behaviour, and that's where B-trees came from. Extents, run length encoding, so you didn't have to have a bit for every single free block. All sorts of things like that. File system getting large enough that running file system checkers when you mounted them every time was a bit of a problem. So journaling was invented to avoid those problems. And the file system was getting large enough to use a full 32-bit address space. So we're starting to see 4 gigabyte, 8 gigabyte size file systems, and that being a limiting factor. And importantly, with the structure of the hard disks, cylinder group optimizations, so that you had an inode table and a block bitmap, and basically per cylinder group, so that you didn't have to seek between cylinder groups to update the metadata that is associated with a file. So there was locality optimizations appearing. So modern history, early 1990s. I/O concurrency started to become an issue because technologies like RAID had appeared. And so you had a single file system spanning lots and lots of disks. In the early 1990s, SGI was shipping machines that would have 1,000 disks attached to them and a single file system on them. So that was kind of where these things started to appear. Moving on from journaling for crash resilience, as we started to see log-structured file systems. Why write to a journal and then write it somewhere else where you can just have a file system made out of a journal? Yeah, sort of works. And so things were really just, I guess you could say, evolving slowly over time. Most file systems that you saw at the time didn't have a lot of these technologies in them. Usually took 5 to 10 years for these technologies to appear in anything other than a research file system. So in the late 1990s, we started to see some things coming from actual operating system developers rather than research institutions. Soft updates came from, I think it was a FreeBSD developer. And that was a method of replacing journaling by specifically ordering the metadata rights to disk. Now, wonderful concept, horrifically complex. I don't think anybody understands how to do it properly even now. There's things like data transformations, people doing in-place compression. There were a lot of people experimenting with that sort of thing. Encrypting file systems started to appear because the CPUs were starting to get fast enough that you could do these sorts of operations without impacting on your I/O. Optimizations for journals, multiple journals in a file system, wandering logs. Instead of seeking to the journal, you just write right next to the metadata a piece of a journal and link it back to the original journal, the previous piece of the journal, update the super block to point to the new one, and so you didn't have to seek to write your metadata out. And on top of that, there was then file systems starting to do asynchronous journaling, where they would commit a transaction, a change, in memory, not to disk, and then sometime later, checkpoint all of those transactions to disk. And so they did less I/O, a lot faster. I can't do that. Okay, so I guess you could say now current technologies. I started to see file systems that would do transparent error correction. You didn't need to know that there was an error actually in the file system, it just fixed stuff for you. ZFS is probably the best known of those. We started to see file systems again with direct device management, where the file system was responsible for actually managing the drives that are behind it and doing things like RAID across them and so on. ZFS is kind of a step ahead in that case. A lot of these things came out of the work that the engineers at Sun did. But once again, they were building on other file systems that used similar sorts of technologies. They just took it one step further. Then, well, we're now jumped it's 2006, once again, no, 2007, once again at a FAST conference, there was a paper on a reference-counted copy on write B tree presented. Certain people in the Linux community found that interesting, and that's what Btrfs was based on. Now, in the past couple of years really, log-structured merge trees have started to be the hot thing in research and so on, because of the problems that they solve in terms of they work kind of like a log structured file system, but then have the ability to operate similar to a B-tree based file system and the logarithmic lookup behavior that they have. And so they're very effective with lots and lots of small files. So, with all that, let's look at some Linux file systems. In the early days, so we're talking 1991, 1992 here, everything was based on the Minix file system. Minix was used to bootstrap Linux. And so, of course, the first file system that was supported was Minix. Soon after that, probably about a year into Linux's life, the extended file system came along to limit to work around the limitations of the Minix file system, because it was really only a 16-bit file system. So we're already above the limits of 64 megabytes and 64K inodes. So that's where extended file system came along. That was actually quite primitive. That was rocks and clubs. It wasn't very long after that. Well, it was about 6 months that EXT2 appeared, and that fixed a lot of the problems. Yeah. EXT2 fixed a lot of the problems that EXT had. It moved from linked lists for tracking free space to bitmaps, actually block group bitmaps, which was kind of cutting edge at the time. That was using techniques developed in the late 1980s, and also greatly increased the size of the file systems that were supported. That was basically written by Remzi, who also wrote EXT, with help from Stephen Tweedy and Ted Cho. Now, you all know who Ted Cho is, I'm sure. He's now the maintainer of X4, so he's been working on the extended file system family for an awful long time. And the reason why it's been around for so long is that it's extensible. So let's fast forward a little bit. In 1998, X2 was starting to show limitations in the crash resilience, and that was when journaling was proposed for X2 as an extension to it. That was when it was first proposed, not when it was actually completed. In 1999, IBM released JFS under the GPL. In 2000, SGI released XFS under the GPL. So all of a sudden, there's this massive profusion of almost enterprise class file systems suddenly becoming available for Linux. It was quite unprecedented. So in 2001, a year later, we get X3 merged, which is X2 with journaling. Riser 3 was merged. JFS2, the journaling flash file system, was first merged. That was the first major widely used flash file system that came into Linux. And we saw the first stable JFS and XFS releases. They weren't in the tree yet, but that was when the first stable releases were available in distributions. So 2002, we saw both JFS and XFS get merged. 2004, Riser 4 came along. How many people here think Riser 4 is still going to get merged? They're still trying. Yeah. 2005, NilFS appeared. That was the first log structured file system of any note. That was used by Nippon Telegraph Japan in their telecommunications systems. So that was actually an interesting thing, a major Japanese company open sourcing their file system that they used. That was a big moment from that perspective. In 2006, X4 was first proposed as extensions to X3. It was created a month or two later. Btrfs came along about a year later. 2008, there was a whole lot more that occurred. UBFS, another flash file system, was merged in. X4 was declared stable. We'll get to that later. And Tux3 design was published. Now, I don't know how many people know about Tux3, but it was designed to be a Btrfs competitor, a versioning, snapshotting, really, really fast file system. Not much has been heard since. Okay, 2009, Btrfs was merged, but in an experimental state. It was considered still unstable, the on-disk format was still changing, and it was being merged to help the development process. Interestingly, Nilafs 2, the successor to Nilafs, was also merged at the same time, so the Japanese had actually been doing a fair bit of work on it. 2010, Logfs. Now, you might think by its name that Logfs is a log-structured file system. It's not. It's a journaling flash file system. So just to confuse you there. But that was merged to round out a lot of the flash file system support. It solved various problems that others hadn't. Yes, Willie?
There's actually a good reason for calling a journaling file system logfs. That's because JFFS2 is actually a log-based file system.
Yes. Yes. So as Willie just pointed out, JFFS2 wasn't a journaling flash file system, it was a log-structured file system. And so the name, in truly ironic fashion, had to be swapped. And yeah, in 2013, the F2FS file system was merged, which was is a flash-optimized file system designed for multi-channel flash devices, which is basically what all your SSDs are. So that's under active development and actually works pretty well. That's come from Samsung, I think it is, and it's under very active development. It's probably actually stable enough to use. So that's basically a quick overview of how Linux file systems have merged, moved through the times. Now, we do have Linux history in Git trees. If we want to do any sort of analysis, Git tree analysis is always the simplest way of doing it. So there's this version up on archive.org, and it's mostly complete from 2.4.0. Probably 2.4.5 is where the individual commit level, patch per commit starts. But there's a few issues with the way the patches were imported and so on. For example, there's commit date issues. While you do a git log, they show up the correct date, but that's because git log shows the author date and not the commit date. And so the commit date of the commits is 2007, not 1993. And as a result, if you do a search using git log since 1993 until 1994, there's nothing there. It doesn't work. So there's a few issues with the tree that meant I had to do a whole bunch of manual hacking to get the information out of them. There's also XFS, the entire history of XFS from the first commit in 1993 up in a Git tree on oss.sgi.com. I use that all the time, trying to work out why somebody did something in XFS. And after looking at it, I'm usually left scratching my head going, that didn't help at all. Most of the commits are intact. There are some commits where we don't know who the username for the commit. We don't know who it actually was. We don't have an email address conversion for it, so there aren't names associated with them. And some of the commit messages changed over time because it was all converted from internal SGI revision systems, and they changed over time as well. So there was a bit of manual, stuffing around there. So if we look at who wrote what and when, mainly what we're looking at here is the ext file systems, XFS and Btrfs, the ones that everybody's familiar with. I could have done more, but it takes an awful long time to actually do all this, and time is something that I don't have a lot of. So when something happened, you can look at the change lines, diff stats and stuff like that, since, until, and whatnot. So it's easy to work out when something changed or when a big change was made and so on. What comes from looking at the diffs and the commit messages. Sometimes commit messages, even just the subject line, is all you need to know. Other times you actually have to look at the code to try and work out what it was. And I think that the authors of the paper that I mentioned was the motivation, they came across the same problem. They had to actually manually look and classify in the same way. Who did things? Up until, from 2.4.5 up until now, most of the commits have the correct author on them. But prior to that, really, it came down to looking at mailing lists and things like that. So it was very intensive, and I did a lot of Googling to find things out. So from that, who wrote what when? Let's have a look at the ext file system. This is effectively a diff stat. In 1991, 2,500 lines of code were added for ext. Okay? That'll give you an idea of how small the original file system was, how simplistic it was. Around here, there was non-working code removed. It was removed because instead of making it work, Linux said, no, you're not going to do that in our working file system, do it in ext2. And so up here in, I think it was 2.1.21, that was where it was removed from the tree. So that there, it's a 5-year life for it. Okay? And not many people were using it past there. So, look at ext2, who wrote stuff? Okay? So there's a few little things here. The important thing to note here is that the commits associated with Andrew Morton, they're from patches that came through his tree and weren't necessarily attributed correctly to the person that sent them. Well, most of them were attributed, but the format was so different in every patch as, this came from so-and-so. This patch contributed by, this from, and so on. So there's no scriptable way of extracting that from the logs. So they came through Andrew Morton, they came from Stephen Tweedy and Ted Cho and all these other people you see. But what's interesting is that the number of names you probably recognise there as modern contributors. And the reason for that becomes apparent when we look at the next slide. Okay. It's a bit hard to read the small text here because of the resolution limitations, but basically next to, there's a bunch of work done when it was first committed, and that was, the first commit was Remy Card, did all the work, and then Stephen Tweedy did all of these allocation changes, block pre-allocation, goal-directed allocation, directory read-ahead, stuff like that. That appeared there. There wasn't any other feature work done on ext2 for another, 4 years. It was basically just maintenance work in between. And then there was a bunch of work done by Ted Cho, which was directory file type optimizations that came from BSD. Stephen Tweedy with directory block pre-allocation and so on. Step forward another 4 years, okay? And then there's more work done here for more features added. There's bits and pieces like that, and they came from people like Alviro and Andrew Morton and whatnot. And they were actually during the 2.5 cycle of the kernel. So things like the introduction of direct.io and the modern bio interface that we have rather than using buffer heads all the way down and whatnot. So this is where a lot of infrastructure work was done. Interestingly enough, this big piece here, okay, that's about the time that, once again in the 2.5 series, we'd had XFS merged. This is for extended attribute support and ACCL support. Now, that came from Andreas Grunbacher, Christoph Hellwig, and the XFS team. That's what the commit message says. I don't know who the XFS team was at the time, that was before me. But what we're seeing there is that functionality that's come from XFS when it was merged is now being pushed back into all the other file systems as generic infrastructure. And so we're starting to see cross-pollination from the different file systems. So the only other major change, reservation window-based block allocation, was a backport from ext3.
What about the all-log allocation?
Pardon?
What about the all-log allocation?
That's in there.
Okay.
That's only 20 lines of code, really. It's very, very small change. It changes an index goal, so it's not a lot of code to do that. And so if I started commenting about every 20-line change, yeah. So you can see that there's certain names that show up, and they'll show up again when we look at X3. Same problem with the commits, Andrew Morton. Probably half of that number actually were written by Andrew himself. Because once again, there was a lot of work being done in the 2.5 series, in the memory management system and write back and whatnot. And so that was where a large number of those changes came from. Interestingly enough, Alviro and Christoph Hellwig, most of those changes are actually VFS level changes. They're not actually file system specific changes. And so what we're seeing here is that in ext3, after a certain period of time, there hasn't been an awful lot of change in it. Most of it, again, has been maintenance. So if we look at that, rename from ext2 to ext3, do all the changes to add journaling. That was Stephen Tweedy. And so we had Andrew Morton, Stephen Tweedy, Ted Cho, and others doing all of that work. And then we've got the H3 directory indexing, extended attribute support at the same time. And as you can see, there's a lot of change at the start, and it just slowly drops off. And there's not a lot of change in this long tail. Okay? This outlier out here, that's actually files being moved around. That was the, I think, the UAPI changes and moving the ext3.h header from include Linux, ext3 back into FS ext3. And so really, there aren't much changes going on other than maintenance. And so when we go back to look at the original motivation, this is one of the reasons why a lot of the analysis was done on bugs. Because there are a lot of bug fixes in here. They don't result in much lines of code change. So by ignoring features, which are all of these big spikes, what they actually did is take a filter and filter all of these little things in there and then analyze those. So it's a different view of the life of the file system. So let's move on to ext4, something that is completely in the 2.6 tree. And so these are all accurate. So what we see, Ted Cho, who's the maintainer, you'd expect him to be high up on the list of committers for ext4. Jan Kara works for SUSE and does a lot of VFS and ext3 and ext4 work and so on. Anish Kumar works for IBM. Eric Sandin works for Red Hat. Lucas Zerner works for Red Hat. Dmitry Monakov, he does OpenVZ work. Teo Ma works for a Chinese company, Taobao, I think. They're the big search engine over in China, and so on. But as we end up down the bottom here, 54, 52, Alviro and Christoph Hellwig. All the VFS changes that have occurred. So you can see here that there's a lot of development. We see all of the development work on top of how much maintenance work is showing up in the file system. So when it comes to looking at feature work, this is very, very different. All of these peaks are features being added to ext4. Okay. This is very different to ext3. There is no long tail on it. There is continual addition of new features into ext4. Now this green line here, that was where ext4 was called stable. Okay. Where are we? That one there. Okay, so that line there, that was where they fixed the zeroed files after crash problem. Just saying. But what you see here, I won't go through all the changes, but what I will point out is that there's ongoing development. The development of the file system has not stopped. There's new features going into it all the time. So when somebody says that ext4 is stable, it might be stable from the perspective of there's no new regressions in it, but all of these new features are adding new flags into the file systems, changing on disk formats, doing all sorts of interesting things. So the code is in no way a stable, unchanging base like we've got with X2 and X3. So it's actually moving quite quickly. Btrfs, which we know is still under active development work. A lot more commits gone into Btrfs, which is not surprising because it's got about almost 2.5 times as much code in it now as X4. Btrfs has passed the 100,000 lines of code. It's now actually bigger than XFS. We'll get to that a little bit later on. But once again, we've got Chris Mason and Joseph Basic. I always have problems with his name. Basic. Those two are the two main protagonists. They're now working, I believe, for Facebook. And they've done a large amount of the development and bug fixing that's been going on and so on. But what is interesting when you start to look at the timeline of features, okay? We'll start with pointing out that there's a big gap in the history here. This is where Btrfs got merged into the mainline kernel. But before it got merged, there was a problem with the Git tree, and so it had to be rebased to fix a problem. And remember how I mentioned that the Git tree history for the archival stuff had this author date, commit date problem where the Git log shows the correct date, but the commit date is 2009, March. So when you actually do date-based searches, that's what you get. Nothing actually happened in those 18 months. But if you do a manual Git log, they show up as the correct dates. So this information here, these changes here, extent-based page cache, extended attributes, data equal ordered, online resize, directory backrefs, RAID 10 support, multiple devices and so on, they all happened at different points in time in that log. It's just, I left it like that just to point out just how much work is actually going in, and that's plus 25,000 lines. So there's a lot of work that went in. And the interesting point here is that they're all additions. Okay? There's one outlier over here, but over time, the Btrfs code base has only ever grown. So all of these commits in this area here, they're mostly Joseph and Chris. But as we move forward in time, what we actually see is a whole bunch of different people starting to show up. Lee Zephan, Arne Janssen, Stefan Behrens, Lee Zephan, Arne Janssen, Stefan Behrens, Ilya Dromov, Stefan Behrens, Joseph, Stefan Behrens, Louis Bow, Chris Mason, Joseph Basic, Stefan Behrens, Mark Verhesh, Joseph Barrett. So you see these names actually start to change over time from all the development being done by Chris and Joseph to a whole bunch more of common contributors and regular contributors. So you can see the actual developer base grow. And it's an interesting way of looking at it. And you don't see this through looking at bugs. It's when you start to look at the features and see the large contributions that these sorts of patterns appear. What other pattern here actually is quite striking? Has anybody noticed the pattern? Not that it's growing. It's going up and down, up and down, up and down in a fairly regular cycle. Every third month, actually. What happens every 3 months? Exactly. The merge window happens every 3 months. So what you're actually seeing there is the active effect of the Linux development cycle over time. Merge window, fix, 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 fix. Merge window, fix, fix, fix. Merge window, fix, fix, fix. That pattern is basically all through the whole thing. And if you go back and look at the X4 pattern, give me a moment here. Look at that. Merge, fix, fix, fix. Merge, fix, fix, fix. Merge, fix, fix. Merge, fix, fix. And so on. It's the same 3-monthly cycle that happens through the development pattern. Start to see interesting things when you look at this sort of code. Anyway, XFS. I didn't get to the top, huh? Oh well. But Christoph, long-time contributor, myself. The interesting part of looking at this is that we've still got the same number of commits from VFS updates, but there is a large number of other people. Interestingly enough, we've got several people that, well, the majority of people on that list either at one point in time worked for SGI, which is no surprise because that's where it came from. But none of the people on the list that worked for SGI still work for SGI. And most of those commits have come from outside, you know, after they've been employed by SGI. If we look at the history from 1993 to present, Christoph, yeah, he definitely is still at the top, but there's all these other people in here that show up. Steve Lord was the maintainer from the initial Linux port for up until 2003. So he was the first Linux XFS maintainer. But Doug Doucette, he had the second XFS commit. So he was one of the first guys. Adam Sweeney, first XFS commit. Okay? These guys are the actual architects of XFS. And you start to look at the number of commits that they made and over the time frame that they made them, they were very, very prolific writers. And so now, this is the XFS graph over time. Now, I'll only point out a couple of things. This is where XFS was under major development. Okay? So 1995 was roughly the first release to customers. So that's all development. This was the next version and so on. That was when quota was added and so on. But over time, this is where the release under GPL was announced. This is where it was actually released. This big minus coincides with when they did an encumbrance review and removed all of the code that couldn't be released because of licenses. So you can see how much code got removed at that point. It still worked after that. But that's the interesting thing. On this graph, compared to all the other file systems, there's all these major code removals. There's as much code removal as there is addition in that. Some of these things you can ignore because they're actually relaying out, moving files around in the repository and so on, because that happened over time as 2.4 became 2.6 and various things like that. But you look at some of the things that happen. This big Is it gone? Yeah. So this big removal here. Yeah. Is there anyone from the NSA here? Yeah.
It might be your thing. Like has the thing good.
Nobody knows who I am now. Yeah. So that big removal there was actually the point in time that we added generic read-dir support to use the kernel infrastructure, and we removed all of the internal hash-based inode caching and replaced it with radix trees. So that particular change there improved the scalability of XFS by a factor of about 100, and it removed a couple of thousand lines of code. So we have a history of actually making major improvements, but at the same time removing a large amount of code. And so what we end up with is that all of these small additions are all features, but these here, where code is being removed, most of them are also features being added, or improvements and scalability being added. So it's actually quite different to the other file systems. And all the way up here, we see that there's a large amount of addition occurring there. That's all the metadata CRC work that's been done recently. So that's actually the first time in a long time that we've actually had the XFS code base increase in size. So if you look at those overall, when you lay them over the top of every one of them, okay, it's actually quite interesting. I'll start over here. The Linux file systems, ext and x2, the development started at roughly the same time that XFS did. Look at the amount of work being done that's different. Okay? Across the entire range, until we get to Btrfs, the amount of work being done on XFS is greater than any other Linux file system. Put them all together, it's greater than any of them. So there's been an awful lot of work done there, even though it's a larger code base and probably no more people working on it. There's an awful lot more change happening in it. And so it's just an interesting comparison of how those file systems have changed over time and what's been done with them. Lines added, or lines removed, lines added. So you can see that there are lots of changes. And interestingly enough, once you get into this section of the graph, Btrfs tends to dominate everything else. So, as I said, I'd mentioned total lines of code. These are actually taken from Eric Sandin's website. I haven't had time to update them or ask him to update them. But they give a rough idea of, this is from 3.4, okay, so about mid-2012 these numbers came from. But the progressions have held true, because if you look at the progression for Btrfs, it's due to progress, overtake XFS as the largest file system. It didn't quite happen at 3.8, but it has happened. So those progressions have actually shown that Btrfs is now a larger file system than XFS. So that'll give you an idea of the complexity of Btrfs. And it's still getting more and more complex, and they're still adding more and more to it. So the last thing to look at is who reviewed code. We always talk about people who have added code and so on. We never talk about who's reviewed code. So back, I think it was 2626 or somewhere around that, the reviewed by tag was added and people started using it. Now, what you see here is the people at the top, Christoph, myself, Mark Tingley, Alex Elder, Ben Myers, Eric Sandin, they're all people that work on XFS. Because XFS already had a process that was the equivalent of what reviewed by was. And so all we did was start adding who did track the reviewed by in the commits. And so as soon as it was there, we were already doing it. And so as a result, it's a process that other file systems are only just really starting to pick up and add into their processes. And so that greatly skews the actual numbers. So you can see percentage of commits that have a reviewed by tag on them. XFS actually goes over 100% because that's for commits. You might have 2 reviewers for a commit. There's 2 reviewed by tags for one commit. Some commits might actually have 3 or 4, depending on how complex they are. So it's entirely possible to get a greater than 100% reviewed by rate for a commit. But as you can see, the general trend, even for Btrfs and ext4, is that they are slowly increasing the number of reviewed patches. So the processes that are being involved, that people are using and being pushed, are actually improving as we go over time. And so just a few things that I found while I was looking through mailing lists and code and so on. Truncate is still a pain in the arse.
More than cross-directory rename?
Over history, there are far more truncate bugs than anything else. Just about done. Yep. Secure deletion currently doesn't work. X2 had secure deletion. It never worked. We've never added secure deletion to a file system since. People ask, but they get told no. Ever wondered why fsync sucks? Oh, okay. We can do better than that. This conversation happened multiple times. ext to ext2, ext2 to ext3, ext3 to ext4, and probably soon it'll happen for ext4 to ext5. You can't change the existing stable file system, add another number. And on that note, Question?
So what else is left to remove in XFS?
So the question was, what else is there left to remove in XFS? That's a good question. There probably isn't a whole lot more that can be trimmed, though we are slowly removing. There is still stuff that has been there since 1993 that can be improved. And so the general trend is that we're still reducing the amount of cruft in the code. Yep.
Do you think there's too much emphasis on numbers of commits? I mean, that first study you looked at simply the numbers of commits and you ignored lines of code. Are there other measures that are better?
Okay, so the question is the original study that provided motivation, it looked at commits. Is there a better way of looking at it as commits versus lines of code changed and so on? It really depends on what you want to show. Looking at commits and classifying each individual commit and the type of commit, the lines of code change doesn't really matter in that case. When you're looking for things that have been added to a file system, a big feature or whatnot, that's when looking at the lines of code change actually tell you something. So it depends on what you want to actually talk about. Yeah?
You had listed types of changes, bugs, features, maintenance, etc. And maintenance was a large piece of that.
Yeah.
What sort of thing is maintenance?
Okay, so the maintenance patches were things like cleanups, factoring code, and whatnot. And that was one of the things for the motivation. Why is 60-odd% of the XFS changes considered maintenance? And most of those commits that removed lots of code were considered maintenance. And so the amount of change that was actually done, and also the fact that the lines of code are going down. There's a lot of maintenance going on if you're reducing the size of the code, but not losing any features. Yeah, one more?
Just briefly, with journaling file systems that are designed for Flash, what strategies do they use to minimize the number of erase and write cycles? Because the journaling is obviously pretty noisy.
They tend to use techniques like wandering logs, so the journal is never, you have normal journaling is you've got a circular log, so you just overwrite the tail all the time, all in the one place. Flash file systems, or Flash can generally handle that if there's a wear leveling layer in the hardware or the MTD layer or whatnot. But Flash optimized file systems, they tend to use techniques like wandering logs so that the logs never overwrite the same blocks and they go in with the data and so on, so that they automatically spread across the Flash. So there's techniques like that. Yeah. All right.
Well, thank you very much, Dave. It was a very interesting talk.
Thank you. Thank you. Thanks a lot, guys.